Okay, moving on to our next topic. This topic is the higher derivatives. We already uh, calculated some partial derivatives, and we know from our vectorial calculus that how a tangent line to a point in a curved surface in a three-dimensional space is about. Now let's do this brief explanation of what once you are confident with the partial derivatives, the next level of this is the higher order derivatives. Okay. Uh, let's say that we have a function f, and this function is a function of two variables. Uh, with the textbooks and the most common problems, those two variables are x and y. And we know because we already calculated that the partial derivatives f sub x and f sub y, and those are the result of applying the differentiation to the main function, and those partial derivatives with respect to x and with respect to y, there are also functions of two variables. Because if you see the expression, most of the time you will see there x and y's showing up in your results. So either the main function or the partial derivatives of the main function uh, are a function of two variables. So we can consider that the partial derivatives, let's say f sub x with respect to x, f sub y with respect to y, f sub y with respect to x, and f sub x with respect to y, we can consider this as the second partial derivatives of the function f. If you remember from your lectures or the single variable calculus, in differential calculus, uh, the second derivative is the derivative of the first derivative. In this case, we are applying the same principle, but using the partial derivative method. So if we have some function f of z, fz, that is a function of x and y, then if we are going to calculate the second partial derivatives of this group of variables, then we will use the following notation. All this expression equals the same thing. It's just different ways to represent it. Because you may have a textbook from Louis Leithold, you may have a textbook from James Stewart, you may have a textbook from also Okoski, or the any other uh, Ron Larson, and all these guys they use to represent the partial derivatives in different ways. So uh, the only way that we can have you not to be confused uh, is explaining in this brief summary what the notation are for partial derivatives with different types. Okay, so let's see that this is the partial derivative of a function z with respect to x. So this is equal to the second derivative with respect to x. So this is f sub x. And that is equal to f sub 1, 1. So that means that 1 is the first, in this case, if 1 is here and 2 is here, if we say 1, 1, we are derivating or differentiating with respect to x two times. So we take the first one, and then we are going to recalculate the derivative on the first one. And that is f sub 1 sub 1. That is equal to the partial del dx times the derivative of the function with respect to x. In this case, this is going to be performed first. First, we are going to differentiate with respect to x, and then we are going to again differentiate with respect to x. In some other textbooks, you will see or you will find this type of expression, del square f, which is the second derivative, the second partial derivative of the function, and in the lower part, this is del x squared. That means that it's 2 times with respect to x. So it's the second partial derivative of the function with respect to x and with respect to x. Uh, other other notation is just del square z, which is z is the dependent variable, over del x squared because we are differentiating 2 times with respect to x. Okay, so maybe this will be helpful for you. Let's move to the next one. See, this is the partial derivative with respect to x, f sub x of y. So this is going to be f sub x y, f sub 1, 2. So in this case, we can express it like this. This is del with respect to y times del with respect to x. Why here is switched is because when we do this type of calculations, we do first the x, and then the result, we are going to differentiate that with respect to y. So in this notation, the first step is always inside the parentheses. Another way to express this is this. This is del squared f over del y dx, and this is the same as this one. So the first is going to be the last one, and the last one is going to be here to the right. So this is going to be the first time, the first step, the derivative with respect to x, and then the result we are going to differentiate it with respect to y. Other notation is this, del squared z over del y del x. Okay. The third one is when we have the partial derivative with respect to y and then with respect to x. So this is going to be f of x y, yx, and that is equal to f sub 2, 1. And then if you remember, we are going to place the first operation inside the parentheses and then the second operation outside of the parentheses. So we can have it here the same way. And this is the expression for some other textbooks. And the last one is the partial derivative with respect to y and then with respect to y. This is f sub y, y. So this is going to be equal to f sub 2, 2. And the same dynamic here, f of y, and then again with respect to y. So this is del squared of the function. This is the second partial derivative with respect to y 2 times. And that's the reason why we are looking here at that little superscript. That means that this is squared, but it's not really a power function. It's only saying that we are taking the derivative the first time with respect to y and then again with respect to y. Okay, so I hope and I expect that this is now clear enough for you. Please, you know that you have, I don't know, questions or comments, please let me know. I'm always aware of that, and I will be attending your questions or comments. See you then.